So in the heat of the moment, whenever you're doing some sort of integration, you may not notice that you have an even and odd function. You may not notice also that your limits of integration are symmetric to the y-axis. So let's just see what happens. Let's see what happens when we're confronted with something like this. So we have evaluate the definite integral from negative pi over 2 to pi over 2 of this thing, whatever. Okay, yeah, so let's go ahead and take the integral. Now, I do notice I pick up on the fact that my limits of integration are at least symmetric to the y-axis right there. All right, so we need, oh, look at this guy right here. Oh, look at that. That's when Rowan used to be an axe murderer. Okay, went through a rampage. I think that was through Lowe's. Yeah, that's where that was. Okay. So when I go to do my little integration here, my gosh, can I take it directly? Let's see. Notice that I have a composite function here. Yeah, let's see if we just break this thing up. Let's see if we could do this by using some sort of U-substitution. I'm gonna basically do two different integrals, right? So here's one of them here. And with this one, let's say our U is equal to sine x. I'm choosing that one because you have sine raised to the third power. And your du is equal to cosine x dx, not negative because we're taking the derivative of that. And then I would have to use, actually, yeah, let's keep going. Let's rewrite our limits of integration here. So rewriting our limits of integration, u of pi over 2 is equal to sine of pi over 2, which I'm pretty sure is 1, and then u of negative pi over 2, sine of negative pi over 2, that's equal to negative 1. All right, so then that part of the integral becomes definite integral from negative 1 to 1. Hey, look, notice that those things are also symmetric. I wonder what that means. And that becomes, like whenever I go to rewrite stuff, the sine to the third is going to be u to the third, and then the cosine with this dx, you can think of this as being distributed across this because I'm breaking this up into 2. That's going to be your du. So you have a u to the third, go away, u to the third du. All right, and then let's do the same thing for this one. I'll switch colors to green for this one. I'm going to keep this totally consistent here and let our u, where's that arrow going? I don't even know. U equal to sine x because du is also equal to cosine x dx. And it looks like we could have done this as just one complete integral instead of breaking it up because it is the same du and it is the same u. Okay, well, whatever. Which means that our limits of integration also become this thing right here, our new ones. So plus definite integral from negative 1 to 1. And this time it's just going to be u because it's sine and then its derivative right there is the cosine and then du, right? Because the cosine x and the dx, that becomes our du. All right, let's go back to our blue crayon. Oh my gosh, email's going crazy. It's driving me up the wall. All right, it's u to the fourth over 4, evaluated from negative 1 to 1. And then for the other one, I'm not switching colors. It's not like I'm working for Khan Academy or anything like that. So I'm going to go u to the second over 2, also evaluated from negative 1 to 1. And let's use fundamental theorem here. Plugging in our 1 on the left-hand side, we have 1/4 minus, plug in a negative, I have a negative 1 to the 4th over 4. Let's do the same thing for the other one. 1 squared, this is going to be 1/2, of course, and then minus, I stick in a negative, negative 1 squared over 2. Hey, what's going to happen here? So on this negative 1 to the 4th, of course, that's going to cancel. This is going to make a positive 1/4, and I get 1/4 minus a 4th. Hey, that's 0. Plus 1/2 minus, and then the negative 1 being squared is the even powers also. 0 equals 0. Right? Did you anticipate that? Were you following along this video going, why is he doing that? Because, often what happens is you put an example in a particular lesson, you expect it to go along with whatever the lesson's supposed to be teaching. So if this thing was equal to 0, if this was equal to 0, then this means that it must have been an odd function, because the limits of integration there are symmetric to the y-axis. But how could you have just looked at that? It's like and saw that it was an odd function. Well, the way that you do it is with the algebraic test, of course, and the algebraic test goes like this. I'm going to stick in a negative here. So f of negative x is equal to, I had sine to the third of negative x times cosine of negative x plus sine of negative x cosine of negative x. And now, in order to simplify all of these negative angle measurements that are right in here, you can do one of two things. You can think of the unit circle for them, or you can think of the original graphs for sine and cosine. Let's look at a unit circle. I'm going to make this, because I have access to a sticky and not sticky, a sticker that is a unit circle. Since I don't teach pre-cal, I do teach geometry. I guess I could use it for that. Okay, this is real nice. Okay. So let's do the little sine first. So sine, of course, is the y-coordinate. So if I stick in a negative, it used to go up this way, but now it's going down this way. If we're talking about the y-coordinate, it used to be positive, but now it's negative. So sine cubed of negative x is going to be negative sine cubed. I know that the negative is going to be preserved because I have an odd power that's right there. So that's equal to, so far, negative sine of x, sine cubed of x. Why am I putting parentheses around that? I don't know. And then how about the cosine part of it? Well, so for the cosine part, the positive versus the negative angle measurement doesn't matter, because it's the x-coordinate and it's still on the same side of the y-axis. It's still on the positive x side. So cosine of negative x is still equal to cosine of x, right? Plus, we already talked about this one, right? A positive angle versus a negative angle, positive y value versus a negative y, actually makes this a negative sign. And we already did the cosine 1 as simplifying down to just cosine x. And notice that they both have a common factor of a negative sign, so I'm going to pull that out. Negative times sine cubed x, cosine x, plus sine x, cosine x. And that is exactly equal to negative f of x, which is by definition an odd function. So which one do you do? Do you do all of this, or do you do all of the integration that's right there? I don't know. It just depends. Like, to be quite honest with you, if you had something that looks like this and your limits of integration are symmetric to the x-axis, you're just thinking that it might be a possibility. But in the heat of the moment on the AP exam, it might not be something that occurs to you. Sometimes, though, when you have yourself a polynomial equation and stuff like that, it's obvious whether it's even and odd. But where this could also happen is that there's lots of AP questions that give us a picture of a graph that we're trying to find the area underneath of, and I might just use it in that instance instead, right? So here's the graph, let's say. Let's say that the graph turned out to be, they like to use equations of lines or something like this. Well, it's entirely possible that the area that's right here cancels out with the area that's right there, right? And then likewise, some area over here cancels out with some area over there. And so it's not symmetric to the y-axis, but it has a certain kind of symmetry that you can still use the same kind of technique to speed up, work through that problem just a little bit easier. All right, that brings us to the end of our lesson on both substitution and symmetry. That substitution, I am doing integration by substitution whenever I have a composite function. I have a complicated integrand. I'm going to choose a part of it to be my u. I also do like a du. That thing came from taking the derivative by using the chain rule. And then the symmetry helps me, in some cases, in select cases, speed up the process of integrating a definite integral if we have an even versus an odd function.